Okay, this is going to be the second video on Taylor polynomial approximations for the natural log. Now, if you haven't done it yet, I would definitely watch the first video, but let's just real quickly talk about a little bit of what we went over on that one. Now, again, you've got two possible forms for the natural log. In the first video, we looked at if you just put it in this form, natural log of x. And the graph of the natural log of x looks like this. It was centered at 1, and the reason it was centered at 1 is that the function is undefined at x equals 0. So if the function's undefined, all the derivatives are undefined, and you can't find the Taylor polynomial. But by centering at 1, and again, if you watch the video, we came up with this form of a Taylor polynomial to approximate it if it was in just the natural log of x. Now, what about this one over here? Natural log of 1 plus x. Let's talk a little bit about what that's about. Now, first of all, let's just remind you guys, shifting functions left or right. Suppose I had this. This one right here is the natural log of x. Now, hopefully, you might remember from your algebra days, if you made it be the natural log of, and suppose you put an x minus 1. Now, remember, if you replace the x with an x minus 1, it has the effect of shifting the whole graph 1 unit to the right. So this blue graph would now look something like this red graph. So this would be the natural log of x minus 1. Now, if you wanted to shift it to the left, the only difference is if you want to go natural log of, rather than x, put an x plus 1. And again, remember, that will shift the whole graph 1 unit to the left. So now it's going to look something like this. So that would be the natural log of this one. And that's really all this thing is right here. Rather than x plus 1, it's just 1 plus x. But, and we'll get rid of this. So we didn't shift it to this direction. So all you're going to do is take this one and move it 1 unit to the left. So what that did, the graph used to be here, it got moved 1 unit to the left. So the only difference between these two is if it's natural log of x, you have the blue graph. If it's natural log of 1 plus x, you have this graph shifted, and now it's centered at 0. Again, why would you want to do that? Well, look what it does for you. Is when you had this one, and let's go ahead and get rid of that. On this one, you had the function was undefined at 0. But if you shift it to the left and you've got this now, all of a sudden the function is now defined at 0. So what this means is over here you couldn't center, you had centered at 1 because it was undefined. Now you actually have a choice. If you move it to the left, you can now center this thing at 0, and it'll change from a Taylor polynomial to a Maclaurin polynomial. And the reason you can do that is because now the function's defined and all the derivatives are defined at this point, where they were not over here. Okay. Now, with that in mind, what we're going to do is just run through the same thing we've done before. We're going to start with this definition right here, and we're going to come up with this polynomial and show you how that's derived, and then take a look at what the graphs look like. Then in the third video, we'll actually compare these two and see what the difference is between them. So, just like we've done in the past, now we'll start with this. What we've got is this. Find a Taylor polynomial and the general term for the natural log of 1 plus x centered at 0. Again, just to remind you of the rules, if you have a Taylor polynomial centered at c, it's in this form. If you have the same thing, a Maclaurin polynomial centered at 0, it's in this form. So since ours is centered at 0, this is the definition that we're going to use right here. So the first thing I would always do is just write this definition of the Taylor polynomial down before you start the problem. So we'll take that one right there. Now, if you write it down, it's going to look like this. So begin by just writing the Taylor polynomial centered at 0, which is also a Maclaurin polynomial. Now we're going to do exactly the same steps that we've done in the previous videos. So again, if you haven't done it, I would suggest watching those to see what the process looks like. So our first step has always been to find the derivatives, and we're going to do exactly the same thing here. So find the derivatives. That's going to be step number 1. Step number 2, you want to evaluate the derivatives at 0. So we'll put evaluate the derivatives at x is equal to 0. So second step, just like the other ones. And we'll also do the same thing we've done before. We'll show the work over here, put them in 2 columns, and then move them right across. So on this one, start with the original function, which was f of x. Now, the original function in this case is the natural log of 1 plus x. Okay, now you want the first derivative. We'll get 4 derivatives out of this. So when you do this, the natural log of 1 plus x, remember it's 1 over the argument. So it would be that right there. Then you're going to want the second derivative. So what the second derivative is going to be, now just a little suggestion here when you find derivatives. If you leave it in this form, you're going to have to use the quotient rule. So my suggestion is think of this as being in parentheses to the first power. Bring it up to the numerator, and that will make it be 1 plus x to the negative 1 power. Now, the only reason for doing that is that it makes finding the derivatives easier. So now this one you can use the chain rule on. So it's going to be minus 1, bring the exponent down. Then you've got 1 plus x, but now it's to the negative 2 power. Then times the derivative of what's on the inside, which is just a 1. So now I want to find the third derivative. So what the third derivative would be, again, bring the exponent down. That's going to be 2 times 1 plus x to the negative 3 power times the derivative of x, which is just a 1. And then finally, we'll go ahead and find the fourth derivative. So the fourth derivative of x would be equal to, bring this down, you'll have negative 6 times 1 plus x to the negative 4 power. Now you want to evaluate these derivatives, but another suggestion is it's awkward to evaluate it in this form, so my suggestion is go ahead now and get rid of the negative exponent and put it back in this form again, just because it's going to make it easier to evaluate. So this would become 1 plus x. Then this one would become, you've got a negative 1 on the top, and it's going to be 1 plus x squared. And then this one would be 2 over 1 plus x cubed. And then finally this last one would be negative 6 over 1 plus x to the 4th power. So now I've got them in a form that just makes them easy to evaluate. And again, take each one, come straight across, and just evaluate the derivative, this time at x is equal to 0. So this would be the natural log, and in place of the x, put a 0. So the natural log of 1 is 0. Then this next one would be 1, and replace the x with a 1, or pardon me, with a 0. And that's going to give you 1 divided by 1, which is 1. Then the next one, minus 1 over 1 plus 0 squared, which again is going to become negative 1 divided by 1, or negative 1. And finally plug it into this one, 2 over 1 plus 0 cubed, which again gives you 2 over 1 cubed, or 2. And then finally negative 6 over 1 plus 0 to the 4th power. And the denominator is a 1, so that's going to be a negative 6. So what these are, this is going to help you form the coefficients to the Taylor polynomial up here. So now, just exactly like we've done in all those previous videos, I'm going to rewrite this just because it's going to make it easier to fill in. So in my case, I'll actually just grab a copy of it and move it down. So if I take this and I'll scoot it down, this just allows me to start over again from down here. So I'll move it down to there, get it to right here, and we'll go back to work again. So now the idea is just to fill in these parts of the polynomial. So what I've got is p sub n. So p sub n of x is equal to, again, f evaluated at 0 was 0. So that's going to be a 0. Then I've got plus. Now I need f prime at 0 is a 1 times x. So that'll be 1 times x. Then plus f, the second derivative evaluated at 0, which would be a negative 1. So that's going to be a negative 1 times x squared divided by 2 factorial. Then plus, third derivative would be a 2. So that's going to be 2 times, and it's going to be x cubed divided by 3 factorial, then plus the fourth derivative is -6, so I've got a -6 times x to the fourth divided by 4 factorial. And then plus, and it'll go on and we'll stop after so many terms. So let's go ahead and simplify that now. So what this is going to be would be p sub n of x. And a couple things you can do here. This term is 0, so basically it just disappears. So this would be equal to, now the first term is going to be an x. Then the second term is going to be, this will be a -1, and 2 factorial is 2. So that will just turn into minus x squared. It's like 1/2 of this, or this thing divided by 2. Now the third term is back to a plus again. And 3 factorial is 6. So 2 divided by 6 would be 1/3. So this will become x cubed divided by 3. Then you've got minus, so this next term is going to be a negative. And again, 4 factorial is 24. So 6 divided by 24 would be 1/4. So this will become x to the 4th divided by 4, then plus, and so on. Now, one of the requirements for the problem, let's go back up to the beginning, was in addition to finding the Taylor polynomial, which we've got, find the general term. So let's go ahead and do that. So what the general term is going to be, it's easier if you actually do this. Go ahead and label each one of these. The first term is 1. Second term, 2, n equals 2, n equals 3, n equals 4. If you write it down like that, sometimes it makes it easier to find what this general term is. Now, first of all, it's an alternating series that starts at 1, so you're going to have a -1. Now, the question is raised to the n power or the n minus 1 power. Well, again, you started your series at 1. The first thing is positive, so to make that first one turn out to be positive, you would need an n minus 1. Then the next thing you've got x. Now notice, whatever the term is, that's what the exponent is. So 2 and 2, 3 and 3, 4 and 4, that just tells you that x to the n, because the exponent agrees with the term. And then finally, in the denominator, you've just got whatever n is, that's what you've got, so it's divided by n. So this is going to be the general term. And now you've got the polynomial and the general term. So we're actually done with the problem, but let's, again, just like we've done in the other videos, let's look at some of the graphs and see what this thing actually looks like. So we'll move this up here, and we'll begin to look at the graphs. So what the graphs are going to look like would be this. We'll look at the first several polynomials on it. Again, I'm going to do a couple things here. We'll sort of go through these things one at a time, so we'll get rid of these just for the moment. Okay, and again, here's the original graph. So the original graph was just a natural log that's been shifted 1 unit to the left. Now what we'll do is, just like we've done in the other videos, we'll begin term by term putting these things in here. So suppose we decided to just work with the first term and forgot about all these other ones. Then the question is, how accurate could you get this thing? Where does it stay accurate at? Well, we'll just stick that first one on there. And it looks like this. Now, if you use a y is equal to x, notice it's not very accurate. It doesn't stay very accurate very long. And if we zoom in just a little bit to take a look at it here, it almost begins to separate immediately. So it's like at about 0.1, the blue line and the orange line begins to separate. So this would be accurate out to about maybe 0.1. So now let's do this. Let's bring in the second term. So if you made it a second order, what would it be? How far out could you go? So let's go ahead and put that graph on. And if we did this one, okay, now you get this second order graph, and it should be accurate a little bit longer. So again, let's zoom in, and the question is, how long does the green graph model the blue graph? So if you zoom in, it looks like they are clearly separated at 0.4, but it looked to me like maybe around 0.2 they begin to separate. So this one was accurate out to about 0.2. So we'll add on another term. So suppose you added on a third term. Now how far out could you go and still get a reasonably accurate answer? Let's take a look at that one. In that case, we'll go to a third order. And what that graph looks like is this pink graph here. And now the question is, how accurate is that one? So again, zoom in and take a look. If you zoom in, the pink graph seems to be accurate out to maybe about 0.3 or 0.4. We'll call it 0.3 before you can begin to see some separation between those two. But clearly the pink graph is more accurate than the green graph or the orange graph. So on this one, you seem to be able to get out to about 0.3. And then finally, the last one, suppose you decided to add on that fourth term. So now you're going to do all this. So if you added a fourth term on it, now you'll have a fourth degree polynomial, and it's going to look like this. So it'll look like this red graph right here. But hopefully the fourth order one will model the blue line longer than any of the other ones. So again, let's zoom in, take a look and see what we've got. And sure enough, the red one seems to be modeling it up to about maybe 1.5 or 0.5 or 0.6. I'm going to call it 0.5. So out to about 0.5. So again, as you get in close, you can clearly see the difference between all of them. So let's zoom in just a little bit here. And notice at 5, the red one's the most accurate. The third order, the pink one, the third order is second most accurate. This one's the third most accurate, and this one's not very accurate at all. And as you zoom away from it, all the graphs begin to blend back in. So as you zoom in, they separate. As you zoom out, now watch, the graphs will begin to blend into the blue graph. And if you get far away, they all look like a pretty good model, fairly far away. But up close, again, in general, the higher the power of the terms, and the more terms you use, the more accurate it's going to be. And also, the closer you get to 0, the more accurate it's going to be. So what that is, and we'll pull this thing back down just for a bit here, and go back to our original thing. Okay, so back here. Now what you got is, in the first video we did the natural log of x. Second video we did this one. We came up with this rule for the natural log. We came up with this rule for the natural log of 1+x. And now we just want to put those together. And in the third video, we'll actually do a couple of examples and show you how to actually use these and what the differences are between them.